Have you ever been in one of those group chats, trying to organize something really important like a surprise party maybe, or some complicated trip? Everyone's throwing ideas around, but then someone misses a key message, or their phone dies for an hour, or, the worst two people hit send at the exact same time with totally opposite plans. It just spirals into chaos, right? Okay, now picture that, but scale it up, way up. Imagine the group members aren't people, but thousands, maybe millions, of computers in some huge distributed system, and they all need to agree on one single, absolutely critical piece of data, like your bank balance, right? Or the next command for a power grid, or the real state of some crucial database. If you've got multiple machines trying to update that data at once, and maybe some fail, messages get lost, maybe a network cable gets, I don't know, chewed by a squirrel. This sounds like total, utter mayhem. Impossible.
Hey everyone, welcome to The Deep Dive, your shortcut to being well-informed. I'm Alex, and today we're diving into one of computer science's really fascinating puzzles.
How do we get all these separate systems to actually agree on something, even when everything around them seems to be, well, falling apart?
And I'm Jordan. Yeah, we're digging deep into a really foundational idea today. It's a concept that pretty much underlies how we build reliable distributed systems. And it's an algorithm that, its own creator famously called it difficult to understand at first.
Yeah, not exactly encouraging.
Right. But then in this really brilliant move, he actually simplified it himself later on.
That's the one. We are talking about Leslie Lamport's Paxos Made Simple paper from 2001. This paper is, it's kind of legendary in the field, isn't it? Because it took this algorithm, Paxos, which seemed almost impenetrable, and just stripped it down to its core logic, made it understandable for way more people.
Exactly. Before this paper, Lamport himself said the original Paxos description was, quote, Greek to many readers.
Which really tells you something about how abstract and, frankly, counterintuitive distributed systems can feel sometimes.
It does. And his whole goal with Paxos Made Simple was to show that actually when you look at it the right way, it's, quote, among the simplest and most obvious of distributed algorithms.
Simplicity hiding in complexity. I love that.
And so our mission for this deep dive is pretty much that, to unpack that elegance. We want to break down how a bunch of independent processes, computer, software agents, whatever, can actually reach a single, unchangeable agreement on some value. Even when the network is unreliable, messages get delayed or lost, and computers themselves can just, crash and burn at any moment.
Right. It's all about getting that solid, fault-tolerant agreement, even in environments that are basically designed to be chaotic. Okay, so let's start right at the beginning. What is this fundamental problem Lamport was tackling? What exactly is consensus in this, wild world of distributed systems?
Okay, so at its heart, consensus is really just about agreement. Simple as that. You've got this collection of processes. Just think of them as separate computers or maybe virtual machines or even just software things running on different servers. And these processes, they can propose values. So one might say, hey, let's deposit $100 into account X.
And another one shouts, withdraw $50 from account X at the same time.
Exactly. So the fundamental task of a consensus algorithm is to make sure that out of all these competing, maybe conflicting proposed values, only one single value gets chosen. And that chosen value becomes the single source of truth for everyone in the system for that specific decision. It's the final word.
Okay, give us another example, maybe something really concrete, just to nail that idea down. Beyond banks.
Sure. Think about a massive online game. You've got thousands of players running around, or picking up items, changing their gear, trading stuff. Every single one of those actions needs to be recorded consistently across maybe dozens of servers spread all over the world.
Yeah, you can't have someone pick up a sword on one server, but on another server, it looks like they picked up a shield or someone else got the sword.
Precisely. That would be chaos. So a consensus algorithm makes sure that when a player picks up that rare sword, only one proposed update for that specific item slot gets chosen and copied everywhere. It keeps the game world consistent and fair.
Okay, got it.
Or think about shared configuration services, like Google's Chubby or Apache Zookeeper. These things act like a central brain for lots of different applications in big cloud setups. They use consensus to make absolutely sure that all the different services using a configuration always agree on what the current settings are. You avoid one part of the system working with old rules while another uses new ones.
That really clarifies the stakes. So if the goal is reaching this single agreed upon truth, what are the absolute, non-negotiable rules, the ground rules for any decent consensus algorithm? Because in those examples, getting it wrong just isn't an option. You absolutely cannot have two different realities coexisting.
You nailed it. Safety.
Yeah.
Safety is job number one, non-negotiable. The paper lays out 3 really clear safety requirements. These must always hold true no matter how bad the network gets or how many machines fail. First, only a value that has been proposed may be chosen.
Okay, that makes sense. No phantom values appearing out of nowhere.
Right. It has to come from a legitimate source within the system. No magic numbers, no malicious inputs getting chosen accidentally. Second, and this is really the core of consistency, only a single value is chosen.
The one truth rule.
Exactly. This is what stops you from having 2 different balances for the same bank account or 2 players owning the same unique game item. Once a value is chosen for decision number 135, no other value can ever be chosen for decision 105. It's locked in, immutable.
Okay. One proposal, one choice, one truth.
And third, a process never learns that a value has been chosen unless it actually has been.
Ah, no false alarms. Don't tell me we agreed if we didn't actually agree yet.
Precisely. Prevents false positives. Imagine a server thinking a critical transaction was finalized when it wasn't, and then acting on that bad info. That could cause a disaster cascade. This rule is about demanding absolute certainty before anyone acts on the outcome.
Okay, so safety is all about correctness. Being right, being consistent, avoiding screw-ups. But a system also has to, do stuff. It can't just sit there being safe but useless. That's where liveness comes in, isn't it? The idea that it doesn't just get stuck forever trying to agree.
That's exactly right. Safety is about never doing anything wrong. Liveness is about eventually doing something right. And the goal here is kind of twofold. First, some proposed value is eventually chosen.
Meaning it doesn't just freeze up, it actually makes decisions.
Right. The system makes progress. It doesn't deadlock forever.
Right.
And second, if a value has been chosen, then a process can eventually learn the value.
So once the decision is made, the news spreads. People find out.
Yep. Information propagates reliably, so components can actually use the agreed-upon state.
Okay, and I can already feel the tension there. It's one thing to say only one value is chosen, which, sounds hard enough in a messy network, but then guaranteeing that something eventually gets chosen and that everyone finds out about it. Even when messages vanish, networks split, computers crash and reboot randomly.
Yeah.
That feels like the real uphill battle. It's like trying to get your whole family to agree on a movie for movie night, then making sure the movie actually starts playing, and everyone knows it's playing. Even if the power flickers or the remote gets lost or half the family wanders off and comes back, forgetting what movie was even picked.
That's a perfect analogy. It really captures that subtle difficulty. In these truly distributed setups, even guarantees that seem simple on the surface become incredibly challenging because of all that unpredictability. The network, the individual machines, they're just inherently unreliable.
Okay, so we get the problem. Consensus. We get the goals. Safety and liveness. But, anyone who's tried building reliable stuff knows the simplest ideas often break first. Let's talk about why the easy ways fail. What's wrong with just, putting one main computer in charge of deciding everything? The dictator approach.
Well, that's definitely the most intuitive place to start. And honestly, it works perfectly fine if you assume nothing ever breaks. You could just designate one special process, one acceptor. Proposers send their ideas to this central acceptor. It picks the first valid one it sees, announces it, done. Simple, fast, direct.
Yeah, but the second you said single acceptor, I'm pretty sure alarm bells started ringing for anyone who's dealt with real-world distributed systems. That screams single point of failure.
You got it. That's the immediate glaring flaw. Lamport puts it bluntly. The failure of the acceptor makes any further progress impossible. If that one central machine crashes, or even just gets cut off by a network problem, boom, your whole system grinds to a halt. Nothing new can be decided. And this really highlights that core challenge of distributed systems. How do you get reliability and keep things running when the individual parts are inherently unreliable? You just can't bet everything on one component. That's why we build distributed systems in the first place, for fault tolerance.
Okay, so no single points of failure. We're definitely in a distributed world now. But that world has its own rules, right? Its own assumptions about how things work, how they talk to each other. What's the specific model, the set of assumptions that the Paxos paper works under? Because it's obviously not assuming perfect clocks and instant communication.
Not at all. And understanding this model is key to seeing why Paxos is designed the way it is and why it's so powerful. The paper assumes what's generally called an asynchronous non-Byzantine model. Let's unpack that carefully. Asynchronous means a few critical things. First, the agents, the computers or processes, they operate at totally arbitrary speeds. One might be super fast, another might be slow because it's busy. It might even pause for a long time doing, say, garbage collection. You just don't know.
Unpredictable timing.
Exactly. Second, they can fail. How? By just stopping. They crash. Pow. And crucially, they might restart later. But when they restart, they might not remember everything they knew before the crash.
Ah, like amnesia after a reboot.
Pretty much. And this immediately brings up a fundamental need. Lamport notes, since all agents may fail after a value is chosen and then restart, a solution is impossible unless some information can be remembered by an agent that has failed and restarted.
Okay, so they need some kind of persistent memory,
Yeah.
something that survives the crash.
Yes. This points directly to the absolute necessity of stable storage. Some place where critical information can be stored reliably, even if the power goes out or the process crashes completely.
Like writing it to a hard drive or some kind of non-volatile memory, not just keeping it in RAM, which gets wiped.
Exactly that. It's fundamental for data durability in pretty much any serious distributed system, not just Paxos. In practice, you achieve this with things like writing to disk, often using techniques like write-ahead logging or journaling. You make sure the critical data is safely on disk before you update your in-memory state. Newer tech, like NVMe drives or persistent memory, is changing the game here too, offering faster, durable storage. But the principle's the same. The important state, the promises made, the values accepted, they must survive crashes and be recoverable on restart. Without that memory, consensus across failures just won't work.
Makes sense. What else does asynchronous imply?
It also applies to the network, the communication. Messages can take an arbitrarily long time to arrive. You send something, it might get there in milliseconds, might take seconds, might take minutes. You have no upper bound guarantee.
Okay, slow messages.
Messages can also get duplicated. The network might accidentally deliver the same message twice.
Annoying, but maybe manageable.
And probably the most frustrating part, messages can just get lost entirely. Poof. Vanish into the ether.
Okay, that's rough. Lost messages, duplicated messages, unpredictable delays, crashing nodes. Sounds tough. Is there any good news in this model?
There is one crucial simplifying assumption. It's non-Byzantine. This means that while messages can be slow, lost, or duplicated, they are not corrupted. What arrives is what was sent. And importantly, the agents themselves aren't malicious. They might fail by crashing, they might be slow, but they don't lie. They don't intentionally try to sabotage the consensus process.
Ah, okay, so no traitors in the camp, just unreliable, sometimes failing, but ultimately honest participants.
Exactly. Dealing with Byzantine faults where nodes can lie or act arbitrarily is a whole other level of complexity. Algorithms like PBFT handle that, but Paxos operates in this non-Byzantine world.
That's a huge difference. Malicious actors would change everything. But even without them, just those benign conditions you listed, the arbitrary speeds, the message delays, the failures, that makes consensus incredibly hard. It's not just about one machine dying. It's about the uncertainty. Is that server slow or has it crashed? Is my message lost or just delayed? Did I crash and restart and now I'm totally out of sync? It's like trying to navigate in thick fog.
That's a great way to put it. Uncertainty is the main enemy here. And to manage this fog, this uncertainty, the Paxos algorithm defines 3 different logical roles or classes of agents. It's important to remember, though, that in a real system, one physical computer can, and often does, play all 3 roles at once. This is more about separating responsibilities conceptually.
Okay, what are the roles?
First, you have the proposers. These are the ones who actually want a value to be chosen. They kick off the process. They propose things like set the balance to $500 or execute transaction 123. They're the idea generators.
Got it. Proposers propose.
Second, the acceptors. These are the crucial ones. They're like the voters or the judges. They receive proposals, they vote on them, they accept them. They are the guardians of consistency, enforcing the rules to make sure only one value gets chosen.
Acceptors accept or reject.
And third, you have the learners. Their job is pretty simple. Find out which value actually was chosen by the acceptors. Once consensus is reached, learners get informed so they can update their own state or take action based on the agreed-upon value. They need to know the result.
Proposers, acceptors, learners. Okay, clear roles. Logical separation makes sense. Now, we already established that having just one acceptor is fragile. Single point of failure. So the obvious next step towards making this fault-tolerant is use more acceptors, right?
Exactly. If one isn't enough, let's use a group, a committee. So a proposer doesn't just send its value to one acceptor, it sends it to a whole set of acceptors. And the absolute key rule here, the thing that really makes Paxos safe, is how we define chosen. A value is considered chosen when a majority of these acceptors have accepted it.
A majority. Okay,
Yeah.
why specifically a majority? Why not, say, demand that all of them agree? Or maybe just like 2 or 3. Why is majority the magic number?
This is where the mathematical elegance really kicks in. It's kind of the core insight. The paper explains it very clearly. Because any two majorities have at least one acceptor in common. Let's pause there. Imagine you have 5 acceptors. A majority is 3. Pick any group of 3 acceptors. Now pick any other group of 3 acceptors from those same 5. Those 2 groups must overlap. They have to share at least one acceptor in common. It's a basic property of sets.
Okay, yeah. With 5, any group of 3 overlaps with any other group of 3. I see that.
Right. So the rule continues. This works if an acceptor can accept at most one value. So let's say value A gets chosen. That means at least 3 acceptors accepted A. Now suppose somehow a different value B also got chosen. That would mean at least 3 acceptors accepted B. But because those 2 groups of 3 must overlap, there's at least one acceptor who would have had to accept both A and B.
But wait, you just said an acceptor can only accept one value.
Exactly. So it's impossible. The majority requirement, combined with the accept only one value rule, mathematically guarantees that 2 different values cannot both be chosen. The overlap prevents it. It's simple, but incredibly powerful.
Wow. Okay, that is elegant. The overlap is the safety net. But hang on, that raises another problem, doesn't it? What if you have multiple proposers? Proposer alpha sends value X to, say, acceptors 1, 2, 3. Proposer beta simultaneously sends value Y to acceptors 3, 4, 5. If the rule is just, like, accept the first proposal you get, Lamport calls this the naive P1 rule, right? Then acceptors 1 and 2 accept X. Acceptors 4 and 5 accept Y. Acceptor 3, well, who knows which one arrived first, but it accepts one of them. But in the end, neither X nor Y gets a majority of 3. You're stuck. Nothing gets chosen. It's like a hung jury.
That is precisely the deadlock scenario that this simple accept the first rule P1 leads to. It sounds reasonable initially, but in a distributed world with unpredictable timing, it just doesn't work reliably. It kills progress. So the solution, which might seem a bit counterintuitive at first, is this. An acceptor must be allowed to accept more than one proposal.
Wait, but didn't we just rely on them accepting only one value for safety? How does that work?
Good catch. We need a way to distinguish which proposal we're talking about. So we can't just talk about accepting values anymore. We need to talk about accepting specific proposals. And the way we do that is by giving each proposal a unique identifier, specifically a natural number, a unique, strictly increasing integer. So now a proposal isn't just a value like X, it's a pair. A proposal number, say a 101, a value X, so maybe 101X. This lets acceptors track different attempts or different rounds of proposals. A value is now considered chosen when a single proposal identified by its unique number and its value has been accepted by a majority of acceptors.
Okay, this feels like it's getting, well, significantly more complex now.
But
But I think I follow. We're not just choosing X. We're choosing proposal number 101, which happens to carry the value X, and we need a majority for that specific proposal. But the crucial thing is still consistency, right? How do we guarantee that if proposal 101X gets chosen, then some later proposal, say 105Y, can't also get chosen for the same decision instance? We still need that single value guarantee somehow. This feels like the absolute core of Paxos safety.
It absolutely is. And this is where Lamport's step-by-step derivation really shows its strength. He builds up the safety properties logically, showing how the final rules are almost forced upon us if we want consistency. It starts with a property called P2. If a proposal with value V is chosen, then every higher numbered proposal that is chosen has value V.
Okay, read that again slowly. If proposal NV is chosen, then any later chosen proposal like N plus KV must have the same value, so V must equal V.
Exactly. Once a proposal like 101X gets chosen by a majority, this rule P2 says that if any future proposal, like maybe 105 or 110, also manages to get chosen for the same decision instance, it must also carry the value X. It locks in the value. Once X is chosen, the only thing that can be chosen afterwards for this instance is X. It prevents the system from changing its mind later.
Right, that makes sense. That preserves the single chosen value idea over time across different proposal numbers. But how do we enforce that? What if, in the chaos, proposal 101X is chosen, but some acceptor hasn't quite learned that yet. And then proposer beta comes along with proposal 105Y, and that acceptor, not knowing X was already chosen, acceptor 105Y. That seems like it could still cause problems, even if 105Y doesn't get a full majority itself.
You're right. P2 is the goal. But it's not quite strong enough on its own as an operational rule for the acceptors. We need something stricter that applies before a proposal is formally chosen. This leads to P2A. If a proposal with value V is chosen, then every higher numbered proposal accepted by any acceptor has value V. See the difference? It's not just about chosen proposals now. It's about any higher numbered proposal that gets accepted by any individual acceptor. Even if that acceptance doesn't lead to a majority win for that proposal, P2A says it still must carry the original value V.
Oh, okay. So if 101X was chosen, then no acceptor should ever accept 105Y, even if Y is different from X. It has to accept 105X or nothing at all with number 105. It tightens the screws on individual acceptors.
Exactly. It pushes the consistency requirement down to the individual acceptor level. But even P2A has a subtle vulnerability in an asynchronous world. What if 101X is chosen? Then some proposer gamma, who's maybe slow or was offline, wakes up. It doesn't know X was chosen. It decides to propose 105Y. Now, it sends this 105Y proposal out. What stops an acceptor, maybe one that also hasn't yet learned about 101X being chosen, from accepting 105? Y would violate P2A.
Right. P2A describes what should happen, but not necessarily how to prevent a proposer from even sending a conflicting proposal in the first place.
Precisely. So we need the strongest form, P2B. If a proposal with value V is chosen, then every higher numbered proposal issued by any proposer has value V. This is the ultimate safety guarantee. It says once 101X is chosen, no proposer should even be allowed to issue a proposal like 105Y. They must issue 105. If they issue anything with number 105, it controls the source of proposals.
Yep. Okay, now that sounds hard. How on earth do you enforce P2B in practice? How do you stop a proposer from issuing a bad proposal? Especially when they might be disconnected or slow or just haven't heard the latest news about what value X was chosen. It's like saying, once we agree the party theme is 80s, nobody's allowed to even suggest a disco theme later, even if they missed the 80s vote. How do you police their thoughts?
Yeah, it does sound like thought police, but the mechanism isn't about policing thoughts. It's about ensuring proposers gather enough information before they issue a proposal and getting promises from acceptors to constrain the future. This is where the crucial invariant P2C comes in. P2C is the condition that, if maintained, guarantees P2B holds true. It's a practical rule that makes the whole thing work. P2C states, for any V and N, if a proposal with value V and number N is issued, then there is a set S consisting of a majority of acceptors such that either A, no acceptor in S has accepted any proposal numbered less than N, or B is the value of the highest numbered proposal among all proposals numbered less than N accepted by the acceptors in S.
Whoa, okay. That's dense. Let's try to translate that into like plain English actions. What does a proposer actually do to satisfy that?
Okay, let's break it down. Essentially, P2C tells a proposer what it needs to ensure before it's allowed to issue its proposal, NV. It needs to check with a majority of acceptors. That's the set S. And for that majority, one of two conditions must be true. Condition A is the simple case. None of those majority acceptors have accepted any proposal with a number lower than N. This means the proposer is basically starting fresh, or at least with a high enough number to override any past attempts. In this case, the proposer is free to choose its own value V.
Okay, so if the coast is clear with a majority, it can propose whatever it wants. What's condition B?
Condition B is the crucial one for consistency, it says. If some of those majority acceptors have accepted proposals numbered less than N, then the value V that the proposer must issue must be the value from the highest numbered proposal previously accepted within that majority set S.
So if a previous proposal, say 98Z, was already accepted by some of the acceptors in my majority, and 98 is the highest number they've accepted so far, then my new proposal N, which is higher than 98, must carry the value Z. I'm forced to adopt the value from the latest accepted proposal.
Precisely. This is the mechanism that propagates a potentially chosen value. If a value was already on its way to being chosen, accepted by some, maybe even a majority, any new proposer trying to use a higher number is forced to pick up that same value. It prevents them from introducing a conflicting value.
Okay, that makes sense. It forces convergence. But how does the proposer find out about these previously accepted values, and how does it stop acceptors from accepting other older proposals after it has done its check, but before it issues its own proposal in? There's still a race condition there, isn't there?
Excellent point. This is where the two-phase nature of the Paxos algorithm comes in, derived directly from needing to satisfy P2C. A proposer can't just issue NV directly. It has to do a preliminary phase first. To satisfy P2C, a proposer needs to do two key things, which map perfectly onto Paxos's phase 1. First, it needs to find out what, if anything, the acceptors have already accepted. Specifically, it needs to learn the highest numbered proposal, accepted by each acceptor in some majority, that has a number less than its intended new proposal number N. This is how it discovers if it needs to use condition B of P2C and adopt an existing value.
Okay, so phase one involves reconnaissance, checking the past history with majority.
Right. But that's not enough because of the race condition you mentioned. While the proposer is collecting this info, an acceptor might accept another proposal, say with number N1. So the second crucial part of phase one is that the proposer needs to control future acceptances. Lamport says it needs to extract a promise that there won't be any such acceptances.
A promise from the acceptors.
Yes. The proposer, when it contacts the majority in phase one with its intended proposal number N, essentially asks them, will you please promise me that you will not accept any proposals numbered less than N from now on?
It's locking them down. It's saying, ignore the past, lower numbers. I'm taking over from number N onwards.
Exactly. This promise is the genius of the prepare request. It creates a guarantee that if a majority of acceptors make this promise for number N, then no proposal with a number lower than N can ever be chosen in the future because it can never get a majority acceptance. It effectively disables older, potentially conflicting proposals.
Okay, this is clicking now. The two phases make sense. Can you walk us through the concrete steps, the actual algorithm, the synod algorithm, as Lamport calls it?
Absolutely. Let's lay out the two phases clearly. Phase one, prepare, also sometimes called the promise phase, step 1A. A proposer wants to get a value chosen. First, it picks a new, unique proposal number, N. This N must be higher than any number it has used before for this specific consensus instance.
You got to keep those numbers increasing.
Always. Then it sends a prepare request message containing just this number N to a majority of the acceptors. Think of it as prepare for proposal N, or can I use number N? Step 1B. An acceptor receives this prepare request for number N. It looks at the highest proposal number it has already promised to respond to in a previous prepare request. Let's call that max promised. If the incoming N is greater than max promised, then the acceptor does two things. First, it updates max promised to N and saves this to stable storage. This is the promise. Okay, I promise not to accept any proposal numbered less than N anymore. Second, it sends a promise response back to the proposer. This response includes the promise, implicitly by responding positively. And crucially, it also includes the highest numbered proposal, say accepted, that it has already accepted in phase two from some previous round, if any. If it hasn't accepted anything yet, it indicates that.
Okay, so the acceptor promises to ignore older stuff and tells the proposer about the latest thing it actually voted yes on. What if the incoming N is not greater than the number it already promised?
Good question. If N is less than or equal to max promised, the acceptor has already promised to ignore proposals like N, or even N itself if N equals max promised. Right. So it simply ignores the prepare request. It doesn't respond. This prevents it from breaking its existing higher promise, phase 2, accept, also sometimes called the propose phase, step 2A. Now, the proposer waits for responses to its prepare request, N. If it receives promise responses from a majority of the acceptors, then phase 1 was successful.
It got enough promises. It has clearance to proceed.
Exactly. Now it needs to decide which value V to actually propose. It looks at all the promise responses it received from the majority. Here's the key rule, implementing P2CB. If any of those responses reported a previously accepted proposal, accepted, the proposer must choose the value of accepted associated with the highest accepted among all the responses. It adopts the value from the latest accepted proposal it learned about.
It's forced to carry forward the value that might already be winning.
Right. However, if none of the responses from the majority reported any previously accepted proposal, meaning the coast was clear, P2CA, then the proposer is free to use its own originally intended value for V.
Okay, so it picks its value V based on those rules. Then what?
Then, the proposer sends an accept request message containing its chosen pair, NV, to the same majority of acceptors that sent it promises. Think. Okay, please accept proposal number N with value V. Step 2B. An acceptor receives the accept request for NV. It performs one final check. It accepts the proposal only if it has not already made a promise in phase 1B to ignore proposals with number N. In other words, it checks if N is greater than or equal to its current max promised value.
Wait, shouldn't it be strictly greater? Why greater than or equal?
Ah, good point. It needs to accept if N is equal to its max promised. The promise was not to accept anything less than N. So N itself is okay. If, however, the acceptor has made a promise for a number higher than N, meaning some other proposer swooped in with a higher prepare request between phase 1 and phase 2, then N would be less than its max promise, and it must ignore or reject this accept request for N.
Got it. So if the number N is still valid according to its latest promise, what does the acceptor do?
If N is valid, N is max promised, the acceptor accepts the proposal, NV. It records this pair, NV, in its stable storage as the highest proposal it has accepted, and typically sends an accepted message back to the proposer, and possibly to learners, as we'll discuss.
And if that accepted message is received from a majority of acceptors, then the proposer knows its value V has been officially chosen.
Yes. Once a specific proposal, NNV, has been accepted by a majority of acceptors, that value V is considered chosen for that instance of consensus.
Wow. Okay, that's intricate, but I can see the logic. The promise in Phase 1 clears the way and gathers history. Phase 2 tries to lock in the value, succeeding only if a higher promise hasn't been made in the meantime. And you mentioned efficiency tweaks, like acceptors ignoring prepare requests if they've already promised higher.
Yes, that's crucial. An acceptor doesn't need to keep track of or respond to prepare requests with numbers lower than the highest promise it's already made. That cuts down on unnecessary work and messages. It just focuses on the highest proposal number it's aware of.
But that stable storage thing you keep mentioning seems absolutely critical. The acceptor has to remember its highest promise, max promised, and the highest proposal it actually accepted, even if it crashes and restarts.
Absolutely non-negotiable. That's the memory that ensures safety across failures. If an acceptor forgot its promises or votes after restarting, it could easily accept conflicting proposals and break the whole consistency guarantee. Paxos relies fundamentally on acceptors having durable memory.
What about proposers? Do they need stable storage too?
Interestingly, no, not for safety. A proposer can actually forget everything about a proposal attempt if it fails or gives up. It just needs to ensure that if it tries again later, it uses a new, higher proposal number. It can always abandon a proposal number without breaking safety. This makes proposers more lightweight and easier to manage.
Okay, so we've meticulously walked through how a value gets chosen. The acceptors, guided by the proposers, reach the state where a majority agrees on a specific NV. But then what? How do the other components, the learners, actually find out what value V ended up being chosen? Knowing it's chosen somewhere isn't useful if you don't know what it is.
Right. Learning the chosen value is the final practical step. And there are a few different ways learners can get this information, each with different trade-offs in terms of speed and network traffic. The simplest, maybe fastest way is for every acceptor, as soon as it accepts a proposal, NV, to just tell all the learners about it. Hey learners, I just accepted NV. A learner then listens to these accepted messages. Once it sees the same proposal, accepted by a majority of acceptors, it knows that value V has been chosen.
Okay, direct broadcast from acceptors to all learners. Seems fast, but also potentially noisy, right? If you have, say, 5 acceptors and 100 learners, and 3 acceptors form the majority, that's 100 equals 300 messages just to announce one chosen value. Seems like a lot.
It can definitely be a lot, especially if consensus is happening frequently. That n-squared kind of communication cost, acceptors x learners, can become a bottleneck in large systems.
So what are the alternatives to cut down on that message storm?
Well, since we're in a non-Byzantine world where nodes generally don't lie, learners can trust each other. A common optimization is to designate one or more distinguished learners. Instead of acceptors shouting to everyone, they just send their accepted messages to this specific distinguished learner, or a small set of them.
Ah, like funneling the information through a central point.
Exactly. This distinguished learner collects the acceptances. Once it sees a majority for a proposal, NV, it then informs all the other learners that V has been chosen.
That sounds way more efficient. If you have 5 acceptors and 100 learners, the acceptors send maybe 3 messages to the distinguished learner. Then that learner sends 99 messages to the others. So 3 plus 99 equals 102 messages. Much better than 300.
Right. The communication cost drops significantly, roughly to the sum of acceptors plus learners instead of the product. But there's a trade-off, isn't there?
Yeah, now the distinguished learner looks like a potential bottleneck, or even a single point of failure for learning the value. If it crashes or gets slow, nobody finds out.
Precisely. So a common compromise is to use a small set of distinguished learners. Acceptors send to all of them, they coordinate amongst themselves, and one or more of them inform the rest. It gives you better reliability than just one, without the full n-squared cost. Many real systems use something like this.
Makes sense. Sort of a balance. But what if, despite all this, maybe due to really bad luck with message loss or crashes, a value does get chosen, but a specific learner just never hears about it? Can it get stuck, forever ignorant?
It's possible, though unlikely in a well-functioning system. A learner could try asking the acceptors directly, hey, what's the highest proposal you accepted? But even then, if some acceptors are down, it might not be able to confirm if a majority was reached. If a learner really suspects a value might have been chosen, but it doesn't know what it is, and it absolutely needs to find out now, it can take a proactive step. It can essentially ask a proposer, or act as one itself, to run the entire Paxos algorithm again for that specific consensus instance number.
Like triggering a revote, just to be sure.
Kind of. By initiating a new proposal with a high enough number, it will force the system to either converge on the value that was previously chosen, because of the P2C rule forcing proposers to adopt previously accepted values, or if no value was ever chosen, it will cause some value to be chosen now. Either way, the learner will eventually learn the result of this new round. It's a way to actively force the information out if passive learning fails.
Okay, we've spent a lot of time on safety, making sure the answer is right, only one answer is chosen, and Paxos seems incredibly robust there with all those logical properties and phases. But what about progress, that liveness goal, making sure an answer is eventually chosen? Because I can still imagine this system getting stuck, right? Even if it's safe, it might just spin its wheels.
You're absolutely right to bring that up. This leads us to a classic and somewhat notorious problem in distributed systems: the possibility of live lock. Live lock is different from deadlock. In deadlock, everything stops. In live lock, processes are still active, they're sending messages, they're consuming CPU, but they're not making any actual forward progress towards the goal. They're stuck in a loop of futile activity.
Oh, I think I can see how this happens in Paxos. Remember our two stubborn kids, Proposer P and Proposer QP wants value A. It starts phase 1, gets promises for proposal number 100 from a majority. Okay, good start.
Yep.
But just before P can send its phase 2 accept request for 100A, Q, who wants value B, jumps in really fast. Q starts its phase 1 with a higher number, say 101. It manages to get promises for 101 from the same majority.
Right, and those acceptors, when they promise Q for 101, they are now implicitly promising not to accept anything less than 101.
Exactly. So when P's phase 2 message for 108 finally arrives, the acceptors just ignore it. Because they promised Q they wouldn't accept anything less than 101, P's attempt fails.
Yeah.
So P gets mad. It sees its proposal 100 was blocked. So it tries again, this time with an even higher number, say 102. It starts phase 1 for 102.
And gets promises for 102, overriding Q's promises for 101.
Right, which means when Q tries to send its phase 2 accept request for 101, it gets ignored.
And they can just keep doing this forever, right? P proposes 100, Q proposes 101, P proposes 102, Q proposes 103. They keep successfully completing phase 1, getting promises, but their phase 2 accept requests keep getting blocked by the next higher promise. No value ever actually gets accepted by a majority.
They're busy, they're sending messages, but they're just dueling and nothing gets decided. That's live lock.
That is a perfect description of the potential live lock scenario in basic Paxos. 2 or more proposers continuously issuing prepare requests with ever-increasing proposal numbers, each preempting the previous one before it can complete phase 2.
So this isn't just a theoretical edge case then. It feels like something that could actually happen, especially if you have multiple active proposers or network conditions that favor this kind of interleaving.
It absolutely can happen, and it highlights a fundamental limitation. This isn't just a quirk of Paxos, it relates to a very deep result in distributed computing theory. It's known as the FLP impossibility result, named after Fischl, Lynch, and Patterson, who published it back in 1985. It's a really famous paper. What FLP proved, essentially, is that in a purely asynchronous distributed system where messages can have arbitrary delays and processes can crash, it's impossible to design a consensus algorithm that guarantees both perfect safety and guaranteed termination, liveness, if even just one process might fail.
Whoa, impossible. So you can't have it all. You can't have perfect safety and guaranteed progress in this kind of messy asynchronous world.
Not with deterministic guarantees, no. FLP implies that if you want guaranteed progress, if you want to absolutely prevent live lock, your algorithm must use either randomness or real time, for example, by using timeouts. You have to introduce something beyond the purely asynchronous model.
Okay, so what does that mean for Paxos in the real world? We know it's safe, it won't give a wrong answer, but it can get stuck in live lock. How do practical systems using Paxos actually ensure they make progress? How do they break that duel between proposers?
The standard solution is to break the symmetry. You need to stop multiple proposers from actively competing like that. The way you do this is by electing a distinguished proposer, usually just called the leader. Through some mechanism, maybe another consensus round, maybe using an external service like Zookeeper, maybe even simpler timeout-based heuristics. The system tries to ensure that only one process at a time believes it's the leader and is allowed to initiate new proposals.
So you designate one official proposer. Everyone else just chills out unless the leader fails.
Pretty much. If this single leader is stable and it can successfully talk to a majority of acceptors and it uses proposal numbers correctly, always increasing, it will eventually succeed. If it tries to propose n but learns someone else used n+1, it just sighs, picks n+2, and tries again. Since it's the only one trying to make progress, it won't get into that continuous dueling scenario with itself. It will eventually win and get its proposal accepted.
That makes sense. The leader breaks the live lock by being the sole contender.
But here's the really crucial point, and Lamport emphasizes this. Safety is ensured regardless of the success or failure of the election.
Okay, what does that mean exactly?
It means that even if the leader election mechanism itself is flaky, maybe two servers mistakenly think they're the leader for a while, or the leader keeps crashing and a new one takes over frequently, Paxos still guarantees safety. You might get temporary live lock if multiple leaders are fighting, meaning no new values get chosen. But the system will never choose two different values for the same consensus instance. It will never become inconsistent.
So the leader election is purely for liveness, for making sure things eventually move forward. It's not required for the core correctness or safety of Paxos.
Exactly. Paxos is safe by design, even in chaos. The leader just helps it make progress through that chaos more reliably.
Okay, fantastic. So we've gone deep into how Paxos solves the problem of agreeing on one single value reliably. It's a fundamental building block. But how do we get from agreeing on one value, like command number 135 is deposit $100, to building a whole complex fault-tolerant system, like a replicated database or a distributed file system? Those things need to process a whole sequence of operations, not just one.
That's the next logical step, and it's where Paxos becomes incredibly powerful as a practical tool. Lamport explains how to apply this single-value consensus algorithm to implement the state machine replication approach. This is a really standard, widely used technique for building fault-tolerant services.
State machine replication. Okay, break that down for us.
Imagine you have a program that behaves predictably, like a database server or a simple counter, or even a complex application logic. It starts in some initial state. It accepts a sequence of commands or operations as input. For each command, it updates its internal state and might produce some output. The key property is that it's deterministic. If you give the exact same sequence of input commands, starting from the same initial state, it will always end up in the exact same final state and produce the exact same outputs along the way.
Like a calculator. If I type 5, then plus Abraham, then 3, then again, it always gives me 8. Deterministic.
Perfect example. Now, the traditional way to run this state machine is on one server. But we know that's a bad single point of failure. So with state machine replication, you run the same deterministic state machine code on a collection of servers, multiple independent replicas. The core idea is beautifully simple. All the servers will produce the same sequences of states and outputs if they all execute the same sequence of commands.
Ah, I see where this is going. The challenge isn't running the code, it's making sure all the replicas execute the exact same commands in the exact same order.
Precisely. If one replica processes deposit $100, then withdraw $50, while another processes withdraw $50, then deposit $100, they'll end up with different final balances. You need total agreement on the sequence.
And that's where Paxos comes in. We use it to agree on the sequence.
Exactly. This is the big application Lamport describes. You don't just run Paxos once. You implement a sequence of separate instances of the Paxos consensus algorithm. Specifically, the value chosen by the ith instance being the ith state machine command in the sequence.
So you run Paxos instance #1 to decide the first command everyone should execute. Then you run Paxos instance #2 to decide the second command. Then instance #3 for the third command, and so on.
Forever.
Pretty much. Each server in your replica group acts as a proposer, acceptor, and learner for every single one of these Paxos instances. Instance #1, #2, #3. This effectively creates a distributed, fault-tolerant log of commands that all replicas agree on. That's really clever. It turns the single-value consensus into a way to build a totally ordered, agreed-upon log of operations. Like a distributed blockchain almost, but for general commands.
It shares some core ideas, definitely. The goal is that agreed-upon ordered log.
So in a normal, healthy system using this, how does it actually work? A client sends a command, then what?
Typically, in a running state machine replication system, you'll have one server elected as the leader, again, for liveness. This leader acts as the main proposer for all these Paxos instances. Clients send their commands like update my profile or write this data directly to the current leader. The leader then decides where this command should go in the sequence. It might say, okay, I have commands agreed up to number 134. This new client command will be number 135. It then uses Paxos to get this specific client command chosen as the value for Paxos instance number 135. It runs phase 1, then phase 2 for instance 135, proposing the client's command as the value.
And the Paxos magic ensures that only one command can ever be chosen for slot 135, even if there are network issues or other servers trying to propose something else.
Exactly. The consensus algorithm guarantees that uniqueness for slot 135. Then all the other servers, acting as learners for instance 135, eventually learn which command won the slot 135 election. Once a server learns the command for slot 135, and assuming it has already processed commands 1 through 134, it executes command 135 on its local copy of the state machine. Since the state machine is deterministic, and every server executes the same commands in the same order, 1, 2, 3, 135, they all maintain identical states.
That provides the fault-tolerant replication. Very neat. But what about failures? What if the leader crashes right after getting command 134 chosen, but before 135, a new leader gets elected? How does it pick up where the old one left off? What if there are gaps in the sequence?
That's a great practical question, and Paxos handles this quite elegantly. When a new leader takes over, it might indeed find gaps. It might query the acceptors and discover that commands 1 through 134 are known, and maybe even 138 and 139 are known. Perhaps the old leader started proposing those but crashed. But slots 135, 136, and 137 are empty or uncertain.
Can't just skip them, right? The state machine needs a contiguous sequence.
Correct. So the new leader needs to fill those gaps. It does this by proactively running phase 1 of Paxos for each missing slot, 135, 136, 137. During phase 1 for slot 135, it might discover from the acceptor's responses that the old leader had already gotten a specific command partially accepted, like 2 out of 5 acceptors had accepted it. If so, the new leader must pick up that same command value and propose it in phase 2 for slot 135 because of rule P2C. This ensures it doesn't accidentally overwrite something that was already close to being chosen.
Okay, so it respects the past history found during phase 1. What if phase 1 for a gap, say slot 136, reveals that no command was ever accepted previously by any of the majority?
In that case, the leader needs to put something in slot 136 to make the log contiguous. So it proposes a special no-op command, no operation.
Like a placeholder, just saying, nothing happened here, move along.
Exactly. It's a command that, when executed by the state machine, doesn't actually change the state. It just fills the sequence number. The leader runs phase 2 for this no-op command for slot 136, gets it chosen via Paxos. It does this for all the gaps, 135, 136, 137, proposing either the recovered value or no-op. Once the gaps are filled, it knows the log is contiguous up to, say, 139, and it can start proposing new client commands for slot 140 onwards.
That's quite clever, using no-ops to patch the log. And this relates back to that efficiency point you mentioned earlier, that the value isn't chosen until phase 2.
Yes, exactly. The fact that the value to be proposed is not chosen until phase 2 gives the leader this flexibility. It runs phase 1 just with the sequence number, like prepare for slot 136. It only decides what value to propose, the client command, the recovered value, or a no-op, after it gets the promises and history back from phase 1. This also leads to significant efficiency in the normal case. When a leader is stable in processing commands, it might already have standing promises from the acceptors for a range of future slots. To propose command 140, it might only need to run phase 2 directly, sending the accept 140 client CMD message. This means reaching consensus often requires just that single round trip of messages in phase 2.
So just one message out from the leader, one message back from the majority.
Pretty much, in the common case. Lamport notes this makes the effective cost of executing only phase 2, which is considered essentially optimal for fault-tolerant agreement. You can't really get much faster than that single round trip while still tolerating failures.
Wow, essentially optimal. That's a strong statement. Okay, what about those abnormalities again? Live lock if leader election fails. Is safety really still guaranteed if you have multiple leaders trying to propose different commands for the same slot, say slot 140?
Let's be precise. If leader election fails completely and no server thinks it's the leader, then no new commands get proposed. The system halts progress but remains consistent. Safe but stuck. If multiple servers mistakenly think they are the leader, they might both try to propose a command for slot 140. Server A proposes 140 CMDA. Server B proposes 140 CMDB. This can lead to the live lock we discussed. They might duel with prepare requests like prepare 140 or prepare 142, and neither CMDA nor CMDB actually gets accepted by a majority for slot 140. Again, progress halts for new commands. But crucially, Paxos still guarantees safety. Because of the rules, especially P2C forcing proposers to adopt previously accepted values, it's impossible for both CMDA and CMDB to be chosen for slot 140. At most, one of them can ever be chosen. Lamport states clearly, 2 different servers will never disagree on the value chosen as the ith state machine command. Live lock might happen, but inconsistency won't. Safety holds.
That's the bedrock, safety above all else. One last thing on the practical side. How do you change the actual group of servers? Add a new machine, remove a failing one. Can Paxos handle that too?
Yes, and quite elegantly, using the state machine replication itself. The current configuration, the list of servers that are part of the consensus group, acting as acceptors, etc., can be stored as part of the state machine's actual state. So, to change the configuration, you propose a special state machine command like add server Z to the config or remove server Y from the config.
You use Paxos to agree on changing the Paxos group itself. That sounds wonderfully self-referential.
It is. Once that change config command is chosen via Paxos consensus for some sequence number K, all the servers execute it. They update their local view of the cluster membership. From command K+1 onwards, the consensus process might use the new set of acceptors for reaching majority. Lamport notes this provides a simple implementation of an arbitrarily sophisticated reconfiguration algorithm. The system manages its own evolution through the very consensus mechanism it relies on.
That is seriously cool.
Yeah.
Using the tool to maintain the tool itself. Okay, let's try to wrap our heads around this. What's the big picture takeaway here? It feels like Leslie Lamport took this problem that seems incredibly messy, almost impossible, getting distributed computers to agree reliably when everything's failing, and he just distilled it down. Show that the core solution can be built up from really simple logical steps. It's not some kind of arcane magic. It's just very careful, very clear logic, derived almost unavoidably, as he put it.
That's exactly it. Paxos, especially made simple, really pulls back the curtain. It shows how if you just rigorously stick to a few fundamental safety properties like P2, P2A, PTB, and you combine that with a clever two-phase commit strategy involving promises, and you absolutely rely on stable storage for memory, you get provably correct consensus. Now, getting it to always make progress, liveness, needs extra stuff like leader election and maybe timeouts to break live lock. But the core algorithm itself guarantees you won't get the wrong answer, even if things go completely haywire. It's a beautiful example of building robustness from unreliable parts through logic.
It really makes you wonder, doesn't it? If a problem that seems as fundamentally hard as distributed consensus can be broken down into this kind of elegant, almost inevitable logic, what other really complex, maybe impossible-seeming problems out there were just waiting for someone to find their made simple paper? You know, maybe there's a simple core truth hidden inside layers of stuff we think is just hopelessly complicated, just waiting for that rigorous, clear thinking to reveal it, whether it's in tech or science or maybe even how we organize ourselves.
It's a great thought. And the principles Paxos laid bare things like majority voting for fault tolerance, using phased commits to handle uncertainty, the idea of proactive promises, ensuring resilient state with stable storage. These ideas didn't just solve consensus. They became foundational building blocks for so much of the reliable distributed infrastructure we depend on today. You see echoes of Paxos or algorithms directly inspired by it, like Raft, running inside huge cloud databases, distributed file systems, coordination services, even underpinning some blockchain technologies. It truly demonstrates the lasting impact of that kind of rigorous foundational thinking in computer science, turning chaos into order through logic.